given the electric field E is equal to this stuff, find the equation of the streamline that passes through the point. And that's this point. So when we want to find an equation for a streamline, we can use dy dx over ey ex. Now you can remember that, or you can kind of just see that these are both, if you look, they're both the rise over the run. They're both slopes. And we're putting them together because then we can get an equation of x's and y's that relate to this specific streamline point. Or streamline, you know, like these are like electric field lines, streamlines, same thing. Like you have, you know, like in, it's hard to explain. Like when you have a charge and they're going out in all these directions, there can only be one point. So that's what we're trying to find. We're trying to find the electric field line, or in this case, they call it the streamline. All right, so anyway, you got dy dx, ey ex. We know the x component and the y component of our electric field, and it's obviously changing as we move through x and y, and that's why we're trying to find this equation. So we'll plug in our components. The y component would be 2x minus 4y, and I'm just distributing the negative. X component is 4x minus 2y. We can treat this as a fraction for the most part and multiply this through. I mean, it's not really a fraction. It's an operation of, it's a derivative with respect to x, but through differential equations, we kind of know that we can like treat them something like a fraction. Minus 2x minus 4y dx. We'll distribute these dy's. Get rid of the parenthesis. I'm going to move the points that have an x with respect with a dy and the y with dx, and I'll show you why. So 4x dy plus 4y dx. I just added this one over. I will add this one over. 2y. This should be a dx. Oh no, I'm wrong. 2y dy. Sorry. It's 2x dx. I'll factor out the 4. I will factor out the 2, because why not? Actually, I'll just leave it as is. It doesn't really make that big a difference. Okay, so now I'll change colors again. Hopefully I'm not changing colors too much. I'm still trying to get used to that. This is an identity of calculus where dy x is equal to x dy plus y dx. And I may prove that at the end of the video, or you can find this yourself online. There's people who've done proofs of this, or you can just take it to be true, whatever you want to do. So 4 dxy equals 2 dy minus 2x dx. We will integrate all of these. Just, now they're all, before I go on, you wouldn't want to integrate, some of you guys may think to integrate right here and just end up with a 4xy. You can't do that because this x is not a constant, right? Similarly with this 4y dx. You can't do that. I did that when I first started the problem and I kept getting it wrong. It's because this x is not constant. You can't treat it like a constant when you do an integration. You'll screw up your math. So you have to do something like this, or find the correct variables before you integrate. So these derivatives will cancel essentially. You'll be left with 4xy. Same thing, you'll be left with, oh wait, that's a y. This will be a y squared. This x will be an x squared. And we will have 1c, constant for integration. Now we plug in our IVP. Plug in point P, call it point P, 2, 3. So x is 2, y is 3. This would be 24, 12, 2, 24, yep, that's a 9, that's a 4, C, it's a 5, 24 equals 5 plus C, and that would be 19 equals C. So then you plug in your C value, because now we know what it is. That's it, there you go. That's your answer. Now for part B. Unit vector specifying direction of E at Q 3, -2, 5. So I'm going to go ahead and write E. Where's E? 4x minus 2. Let me write that on paper and then just copy it real quick. All right. Q is 3, -2, 5. Okay. So E, I'll just write it again, is 4x minus 2, 2y ax plus minus 2x plus 4y ay. And we have Q at 3, -2, 5, and the unit vector is what is in question. So I'll call it E, Q, like that is question mark. So the first thing we need to do is plug in Q for these points, right? Because all this is this is essentially a vector field. So you're going to get, whenever you plug in points of x and y, you will get a varying vector field. So maybe at the origin, your electric field looks like this, or your vector field looks like that. And then maybe you're over here, and it's in this direction, it's a little larger. So that's all it is. Your electric field is not uniform. It's varying over over x and y, whatever that may be, if it's, you know, some sort of coordinates or whatever. So plugging in, we will get E of Q, and that'll be 4, plugging in the x at 3, minus 2, plugging in the y at minus 2, the x minus, in brackets, 2 times 3, oh, whoops, 2 times times 3 plus 4 times negative 2 in the y direction. Simplifying. 12 minus plus 4 in the AX direction minus, I'll leave that out, 6 minus 8 in the y direction. That means that E of Q, the electric field at the point Q will equal 16 in the x direction, and it will equal positive 2 in the y direction. Don't forget this negative out here. Okay, so now we have E of Q, but we want E of Q as a unit vector. So a unit vector is equal to that vector divided by its magnitude. Because all a unit vector is a vector with a magnitude of 1. Or with a, so like let's say this is your original vector, EQ. Your unit vector will just be like this. It's just 1. So if you have like a unit circle or something, it'll fit on there. And it's nice because you can scale it with other things, and it's useful. So now finding EQ, we just take the Pythagoras, right triangle trig, whatever, and that ends up being (16.12). So EQ is equal to, now I divide 16 by 16.12, and I divide 2 by 16.12. I'm not going to write it all out, but just know I'm dividing this by 16.12 and this by 16.12. I'm just doing this to each component, okay? And that results in 0.99 AX plus 0.12 AY. And that's your final answer. And now, I will try to do the proof, and I may fuck this up, but I'm going to try and do the proof of that derivative I did earlier. Or at least a little intuition as to why this equals because I like to do that. I like to try and give you a little bit of intuition as to why we're using certain things. So if you have dxy, that's basically the change in x times y, right? Because that's what derivatives are, the rate of change. So you have, let's say you have a square. And its units are x and y. And then you have a bigger square. So in this blue, you have x and you have y, right? Now in this little piece right here, from here to here, you have dx. And from here to here, you have dy, right? So what we need to find out is what this section of area is. So you can do that. This is essentially what's happening with dxy. So you can do that by taking the area of x, y, wait, x plus dx times y plus dy. And then subtracting it by that inner blue circle. So you can think of the whole entire red square as this. This is the whole entire red square. It's right here. See it? X plus dx times y times dy. And then you can think of the blue square as xy. So if you want just the red part, you would just do that minus the xy, right? So now we know that dxy is equal to x plus dx, y plus dy, minus xy. And now you can continue to evaluate this. Xy plus y dx plus x dy plus dy dx dx dy, I'd say. Excuse me, minus xy. So this xy and this xy cancel, right? So now you are left with y dx plus x dy plus dx dy. Now the last thing is this piece, and when you evaluate the limit of this, I'm not going to do that because I haven't worked through that on paper. I kind of forgot about that part, if I'm being honest. When you evaluate it, it goes close to 0 apparently. But also, another thing that's I think is fine to think about is this is a very small section of x and a very small section of y. So when you multiply those two very small pieces, parts, whatever you want to call them, when you multiply them together, it just makes something even smaller than that, right? So this is much smaller in scale to these two. So we can assume it to be 0. And then you're just left with this, which is what we used earlier. So I hope that that clears everything up. I tried my best. This one's a little complicated, man. It's a bit of a tough problem because you're using identities that you probably haven't seen since like Calc 2 or Calc 1, and yeah, trying to find field lines is like the equation for field lines is one of the lesser, I think, seen problems in this chapter. But hopefully I did it justice. If you liked it, give me a like, subscribe. Thanks.